Grace Thornton, student number 2548989, root group 15 for the fluid mechanics project. I'm in charge of the theoretical calculations.
And my student number is 239491, and I'll be taking you through the experimental part of this project.
Hi, I'm Olekile Nancy 583 and I'll be handling the simulation of the project through Flumex.
Hi, I'm Maria Ramasala, student number 1838832. I'll be going through the comparison of the results, experimental, theoretical, and the simulation.
Okay.
And hi, hello, my name is Matalo Moffat. My student number is 2440372. And what I'll be looking at is basically the interpretation of the results that Maria would have ascertained from the whole experiment as a whole.
Our project is based on problem 3.70 from Potter's Mechanics of Fluids 4th edition textbook. The textbook, which was published in 2011, was also co-written by Wiggett and Ramadan. The problem requires us to determine the height h of the water and piezometer tube 2. This can be used to calculate the pressure in the pipe with the smaller diameter. The problem investigates Bernoulli's equation, which suggests that the pressure difference from point 1 to 2 is a result of the different velocities in each section. However, Bernoulli's equation does not account for any losses in the system. In this project, our aim is to determine how accurate and effective Bernoulli's equation is in real-life situations. To do this, the problem was first solved theoretically, using Bernoulli's equation and the assumptions that the flow is ideal, that there are no losses, viscosity or slipping, and the flow is inviscid with a linear velocity profile. Furthermore, it was assumed that the flow rate of water is constant. The original problem was solved and h was calculated as 0.1984 meters. The input value from the experimental model, presented on the slide below, was substituted into the derived equation, yielding h as 49.23 millimeters, which is equal to a gauge pressure of 481.71 Pascal. By varying the initial diameter of the pipe, the effect on h can be seen. Increasing the diameter decreases the height.
It's not the
For
same
this
height
presentation
anymore.
of the project, recyclable material was used to build the schematic shown in the previous slides, and in applying the methodology also shown in the previous slides, the values were obtained in a form of a data table, and then they were used to calculate the values for the pressure in which we are.
This is the system that was used to investigate Bernoulli's equation. Pipe 0 represents the inlet pipe of 65 millimeters and a length of 275 millimeters with a PVC manufactured material with a roughness of 1.75 micrometers. The constructed part of the system is represented by nozzle 1, which has an inlet diameter of 65 millimeters and a length of 67 millimeters, and nozzle pipe diameter ratio of 0.3462, which represents the diameter ratio between the smaller pipe and the bigger pipe. The smaller pipe, which is the outlet pipe with a diameter of 22.5 millimeters and a length of 120 millimeters. Both the nozzle and the pipe were manufactured from PET with a roughness of 6,600 micrometers. There has to be a pressure difference to induce flow, and the height attained from the experiment gave pressure 1,815.11 pascals and 190.807 pascals at 23 degrees Celsius. The following results were attained. V1 0.2031 meters per second at a pressure of 1.7909 kilopascals. P2 at a velocity of 1.69517 meters per second at a static pressure of 0.448332 kilopascals. Inlet and outlet showed the same mass flow of 0.67227597 kilograms per second. The negative and the positive sign showing inlet and outlet.
Table 1 shows the comparison of theoretical experimental and simulation results. The main focus will be on the flow rate and the pressure drop. Looking at the flow rate of the theoretical model, it is greater than the experimental and simulation flow rate. This is due to the assumptions associated with the theoretical model, of which is assumed to be under ideal conditions and steady conditions, while the experimental takes into account the friction factors and viscous effects. The theoretical pressure drop is less than that of the experimental and the simulation, with the experimental and simulation pressure drop being equal. An uncertainty of 36.45% is evident in the pressure drop comparison between the theoretical and the experimental model, reflecting substantial discrepancy in this regard.
The discussion section interprets results ascertained through theoretical, experimental, and simulation approaches employed in this fluids assignment. Table 1 presents flow measurements and Figure 1 shows performance flow curves for all the models respectively. Figures 3 and 4 show the variations of the pressures and velocities across the pipe respectively.
The results in this experiment echo Bernoulli's principle that an increase in speed of a fluid occurs simultaneously with a decrease in pressure. They also show that Bernoulli's equation